So let us embark our journey. So mobile phase, that is the most important, the carrier gas. Now the carrier gas is actually the transporting medium, and there are certain properties which are to be fulfilled by a gas to become a carrier gas. And the most important property is the inertness. Your carrier gas must be inert, and most of the time, we are going to see in the next table also, most of the time we rely on helium, we rely on argon. But there is certain disadvantage also, there are certain issues also, that these gases are, yes, of course they are very inert gases, but at the same time they are expensive also. So, but ideally speaking, your inert gas, your carrier gas must be inert as possible. Similarly, it must have highest purity possible. That is, it must not have water content. It must not have any nitrogenous content or any sulfur gases. So it must be in the purest form possible, because otherwise it may lead to reaction, it may lead to a stronger interaction with the volatile components. And if it is going to interact with the volatile component, your impurities are going to interact with the volatile component, then it may actually lead to clogging. It can lead to ghost peaks, which we are going to see. So your efficiency will be compromised if impurities are there, because there are always chances of reaction with the impurities. So high purity must be maintained. Similarly, your carrier gas must be non-toxic. It must be non-flammable. Although in certain cases we use H2 also, but again we have to avoid it as much as we can. So it must be avoided. Similarly, the carrier gas must have a consistent flow rate, so that the pressure along the column must be maintained, because the pressure which is maintained at the inlet point, if you maintain the pressure at the inlet point, then you are very sure that you will get the same pressure at the outlet point. For example, if you have 50 psi pressure, if you are a column, for let us suppose you have a column. Suppose you have a packed column here, packed column. We are going to see different columns in the coming slides. If you have packed column, and if the pressure is 50 psi here, and this column is actually packed, because it is a packed column and it contains certain solid stationary phase, and the liquid is impregnated on it, immobilized on it. So if for example you give 50 psi pressure here, then there are chances that you will get close to 50 psi pressure at the outlet. That is, the pressure at inlet must be same at the pressure at the outlet. And this also tells you that your system is working fine, it does not have any clogging. So you have to use a consistent flow rate, and your carrier gas must be compatible with your detector. That is, detector will respond to the carrier gas, because if detector is not going to work in conformity with the carrier gas, then you are unable to get a good chromatogram, you are unable to get a good efficiency, a good separation. So your carrier gas must be compatible, and we are going to see in the next slides that what are the different carrier gas which are compatible and which are not compatible. Okay, so here it is. If you can see that you have helium, a noble gas, and you have an argon, noble gas, the inertness is always there, because they are noble gases. They are noble gases, and most of the time we use these. Here we have written ECD, used with ECD, that is the electron capture detector. We are going to study the detectors in very much detail. We are going to study 3 or 4 of some, maybe 5 detectors in the coming slides, because each detector is specific to a certain set of organic compound, to a certain set of inorganic compound, to a certain set of pesticides. We are going to study in the coming slides. So the helium and argon are the best one. They are the best one, and you can see that helium has good thermal conductivity also. Another feather in the cap. while nitrogen is of course economical and it is inert, but it has moderate flow, and here you can see resolution is an issue. Resolution is not good when you take nitrogen in nitrogen. Similarly, hydrogen has a very good efficiency, but at the same time, flammability is an issue, very big issue. So you have to, most of the time, you have to avoid hydrogen. You have to avoid nitrogen also. So the best one are the helium and the argon. Now the flow rate. For example, if you have a packed column, then the flow rate, advisable flow rate is 20 to 60 ml per minute. Similarly, if you have a capillary column, which is thin column, although these capillary columns are very thin, but they are very long. They are more efficient as compared to these packed columns. These packed columns are small columns. These are small, and these are long columns. They are less efficient. We are going to see it, less efficient. They are more efficient. More efficient. We are going to see it. We are going to study these in very much detail. Here you can see the rate. It is 1 to 5 ml per minute in capillary. So why the flow rate? Again, you have to recall the Van de Meter equation. You know the famous Van de Meter equation, H is equal to A plus B upon U plus Cu. So U is actually the mobile phase velocity. Here the carrier gas velocity, that is U. So we have to be cautious. We have already, worked on it. So carrier gas control and regulation. Now the carrier gas, which is preferably helium or argon. So with carrier gas, you have to have good flow controller, rotameters. And the role of these rotameters is to adjust the gas velocity or the gas speed. Because if you have to maintain a very good optimum speed, not a good speed, but optimum speed. We have already discussed that what optimum speed is and how it is going to affect different terms and how it is going to affect the overall column efficiency. So similarly, you have to have good pressure regulators to maintain a stable supply, to maintain a uniform supply of your carrier gas. Then you have to adjust the gas velocities, and again the most important one, the purifiers, to remove moisture, to remove impurities, so that your column remains clog free. Okay, so your column remains clog free, that it should have a very smooth flow of your carrier gas along with the solute molecules, along with your volatile solute molecules. So again, why they are important? Because they ensures the consistent retention time and peak shape. Because, and ideally you have a Gaussian shape, and sharp peaks. We have already discussed it, sharp peaks. So what is the effect of flow rate? That if your carrier gas velocity, if your flow rate is less, then you will get broad peaks like this. And if your flow rate is very fast, then you will get like this. So you have to maintain an optimum flow rate. Okay, that is U. You have to maintain optimum U, that is flow rate. Flow rate of carrier gas. And this carrier gas is mainly helium or it may be argon. So carrier gas, because this regulation of carrier gas is important. Because if your carrier gas is not regulated, then the efficiency will be compromised. Okay. So sample injection system. Now this is actually the one of the main important aspect, because for an efficient separation you have a very good sample injection. Your sample must be appropriately injected into the column, into the port where it gets mixed, and then it travels to the column. So your sample must have your sample size must be appropriate so that it can get mixed well with the carrier gas and it can travel, and it must have uniform size. We have seen the effect of size also. So the same principle holds good in GC also, which we have discussed in the elution chromatography. So what is the objective? That you have to have a uniform sample size, accurate, and your sample must be in the vaporized state so that it can mix well with the carrier gas stream. So what are the requirements of your sample? That your sample size must be uniform, it should vaporize instantly, and you can use reproducible injection volumes, that each time you make sure that each time you are using the same volume, and your sample, your vaporized sample is not going to decompose at the operating temperature. Okay, at the operating temperature of the sample injection system. And you have to keep an eye that how much sample you are actually introducing, because if you are going to introduce a large amount of sample, then you are actually loading your column too much, and this extensive loading of your column will compromise the efficiency of the column. Because if you are using a packed column, then there are chances that you can use a large amount of sample. But for a capillary one, the capacity is very small. So if you load an extra amount of sample, then actually you compromise your capillary column. So you have to keep an eye on the injection volume, that how much volume you are using. And most importantly, this is the most important feature, that your sample injection system, your sample injection port must be maintained 50 degree, at least 50 degree above from the boiling point of the least volatile component. Okay, for example, if you have a 3-component system, A, B and C, which are present, these are present in your volatile sample, and this A has a boiling point of, for say, 60 degree, this has a boiling point of 80 degree, and this is a boiling point of 110 degree. Then your sample injection port must be maintained at how much degree? It must be maintained at least 160 degree. That is 50 degree above, least volatile. Okay, so you have to keep this in mind. Now there are number of injection systems, depending upon the type of sample which we are going to study, the type of sample which we are going to identify, the type of sample which we are going to separate. So there may be split injector type system, we have a splitless injector type of system, we have an on column injector system, sometimes we also have a PTV system, that is programmed temperature vaporized system. But these system, that is programmed temperature vaporized system, is actually very specific. So we are going to study these 3 systems which are commonly used, that is the split injector, that is the splitless injector, and the on column injector separately, one by one. So let us start with the split injector system. So this split injector system is generally used for high concentration systems. So here the beauty of this split injection technique is that it is commonly used for the separation of most of the organic compounds, but at the same time it is not good for the trace system. Okay, so it is good for analyzing high concentration, and the good thing is this, that here you can actually use a split ratio type of technique. Okay, that is you can use 1:10 or 1:100 technique. And what is 1:10 and 1:100? That you actually, this ratio tells you that when you introduce your sample, your vaporized sample, then 1:10 means that one part is going here in the column and 10 part is actually venting out. 10 part here, 10 parts venting out and one part is going. Similarly, if it is 1:100, then 100 part will be vented out. So because of this venting facility, your column does not get clogged, your column cannot be packed beyond their capacity. So your column remains compatible. And because of this, you can always avoid overloading of your column, you always avoid clogging of your column, and at the same time, it gives you a very fast analysis. And you get ideal sharp peaks, the Gaussian peaks. And this split injection technique is useful for most of the organic compounds. Generally used technique. Generally used for most of the organic compounds. Okay. So it prevents column overload. Okay. Now there are certain disadvantages also. Number one disadvantage is that it gives you a lower sensitivity. Okay, it gives you lower sensitivity, and again, it is not suited for trace analysis. Although this venting is very beneficial. Okay, this type of this venting is only specific for this split injection port or split injection technique. Now, as the name suggests, here there is no venting facility. All of you have to do, you have to insert your sample directly here. Okay, so here it mixes with the carrier gas and then it travels along the column. And in the column here, actually the partitioning takes place. Here, what happens is, you insert your sample. Initially, you insert the sample in the column and the vent closes initially, but after a certain time it opens, and the moment this vent opens, it becomes a split one. It becomes a split injector. Okay. And initially, when the vent is closed, then almost 80% of the sample goes inside, and after that the vent opens, and when the vent opens, the remaining sample goes. Again, it is good that it is not going to overload your system. Okay. The beauty of this splitless is that it gives you very high sensitivity, and it is very suitable for environmental and biological samples. But at the same time, it has also some disadvantages. That is, it gives you longer analysis times. You have to run your sample for a long time. It takes hours sometimes. And again, it gives broad initial band. Because broad initial band is generated because initially your whole sample goes at once. Your sample goes at once, and because of this, a broad band is obtained. Okay, so in broad band initial occurs because your sample goes straight, and then after a certain time it's vent open and it becomes a split injector. So for an ideal injection, your band should be minimized. The band broadening should be as small as possible, and it is good for the low analyte concentration, while the split one was good for high analyte concentration. Okay, then comes the third one, and this third one is the on column injection technique. Okay, this is something very good, where we have thermally labile compounds, because here you actually introduce a sample straight to the column, so there is no chance of degradation, and that is why this is good for thermally labile compounds. Otherwise, there are chances that your sample gets decomposed by the high temperature, because we know that you have maintained your temperature at least 50 degree above the most labile one. So if you think of this one, then here a lining is there, a lining is there, but such lining does not exist here. Here you are going to introduce it straight in one go. So the sample directly gets injected into the column without vaporizing in the injector port. The beauty of this, that it is very rugged, very robust, and it is very easy to handle. A new person can use this on column type of injection, because you actually introduce your sample onto the head of the column. Okay, so straight. Again, you have minimal thermal degradation because your sample is not getting decomposed, as it does not have to stay in any system or in any port, or it does not have to, you can say, experience the high temperature. So because it goes straight, it has very less travel time, and it is accurate for sensitive samples. So there are limitations, and the one major limitation is that you have to require clean samples. Otherwise, what happens is, because here there is no filtration mechanism, so if some impurity is there, it will directly go into the column, and again there are chances that this column or your impurity gets an interaction, or it gets reacted with the stationary phase of the column, or with the maybe with the carrier gas. If it is, for example, if it is hydrogen, then there are chances. For example, if your sample contains a little amount of water, and if hydrogen is the carrier gas, then it can lead to explosion. It can form explosive mixtures. So what you have to have, you have to avoid any impurity. That is, your sample must be as pure as possible. And another thing is that the control is not very precise here. Unlike here the control is very good, and it was very best for the low analyte samples, for the low analyte concentration. So each of these technique, that is the split injection technique, then the splitless, and the on column injection, each one has certain advantages and certain disadvantages. While deciding the column, the injection port, you have to first look at what type of sample you are actually wants to separate, which type of vaporized samples you have been given to you for separation. So you have to keep in mind, and on the basis of the nature of the sample, the vaporized sample, you have to decide that whether you go for on column injection technique, whether you go for split one, or whether you go for splitless. Okay, so we are going to see in the next slides that this GC technique is very specific in terms of the taking which type of injection port we are using, which type of detector we are using, and which type of stationary phase and which type of carrier gas we are using. And as we have discussed in the previous slide, that conformity between the components, between the 6 components which we have described in the previous slide, the conformity is very important. So each component should work harmoniously with another component, and that work harmoniously with another component, so that your full system must be harmonized to achieve a best separation. Okay, so you have to keep this in mind. Now, after this carrier gas, okay, so we have covered the carrier gas, we have covered the sample injection system, and now it's the time to strike on the heart of the column. So we are going to study the different columns, which are actually 2 types, in the coming slides. So with this, we are finishing the sample injection port, and we have already discussed the split injector, splitless injector, and on column. And I have also given you an idea that another important, that is PTV, that is the programmed temperature vaporized system. That is very specific, and it is used in exceptional cases where your sample is very volatile. So you actually use temperature as a tool to separate different components on the basis of the difference in the partition coefficients of the different components. Thank you very much. Thank you.